Happy learning! Today we're going to talk about matrices. So what is a matrix? A matrix is a rectangular array of numbers. All right, so it's going to look like a kind of a grid filled with numbers. Data in tabular form can be sorted into matrices. So that's when we're going to use them, or how we're going to apply them. Sorry, stored in matrices. All right, and so that's gonna be our big application for these. So for example, suppose we had data on the exports and imports of various countries for various objects. All right, so we're going to have cars, trucks, and parts in the countries Canada, Japan, and Mexico. All right, and so this is all going to be in tens of thousands. Or sorry, in thousands. So Canada exports 13,000 cars, 12,000 trucks, and 32,000 parts. Japan exports half a thousand, so 500 trucks, 0 trucks, 500 cars, 0 trucks, and 2,000 parts. And Mexico, 3.5, 1, and 12.5. All right, so here we have data on the exports, and we also have data on the imports. All right, so the same 3 objects, same 3 countries. All right, we could store these data in matrices. All right, so I'm going to call A matrix that just has this information here. We're not going to care about the titles or the countries. We're just going to have the 3 by 3 of values. So A is going to be 13.5, 3.5, 12.01, 32, 2, and 12.5. This matrix captures all the information of the exports. And B will be the matrix over here. 36.5, 43.5, 14, 12, 110, and 20, 16, 25. All right, so the rows in our matrices correspond to countries, at least in this example. So when we go left to right, those are rows. Rows go left to right. Each row corresponds to a different country. And then the columns up and down correspond to the different items. All right, this first column here corresponds to cars, and then trucks, and then parts. So each column corresponds to a different item. Okay, in general, our matrix, we're going to write, it's going to be A equals, and then the entries, typically we're going to write with lowercase a. All right, so this will be A11, that's the top left entry. And then as we move across the row, we have A12, dot, 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 until the last entry, which we're going to say is A1N. As we go down the column, our first entry is going to be switching. So we have A21 all the way down to AM1. This would be A22 all the way to A2N. And then the bottom right entry is AMN. All right, so the number of rows is M. And the number of columns is N. We say that A is an M by N matrix. Number of rows, X. Okay, this is not multiplication. It's literally just the letter X. Number of columns. Okay, so this matrix here is a 3 by 3 matrix. If M and N are equal, like we have here, then it's a square matrix. Right? Why is it a square matrix? Well, it looks like a square. All right, so let's just look at a quick example. All right, so suppose we have the matrix 1, 3, 2, 4, 1, 2, and another matrix 1, 2, 3, 4, 1, 0. We want to find this is called the size of the matrix. So we want to find the size of both these matrices. C is a 2 rows by 3 columns. Is a 2 by 3 matrix. D is a 3 rows, 2 columns. D is a 3 by 2 matrix. So if we'll see, we might have a matrix where everything is 0. So any matrix in which every entry is 0 is called a 0 matrix. All right, neither of these are 0 matrices because they have some non-zero entries. But for example, this is the 2 by 4 0 matrix. So we'll see there's going to be times where we want to switch the rows and columns of a matrix, and that's called the transpose. So when the columns and rows of a matrix A are interchanged, to create a new matrix so if we switch all the rows and columns of A, so instead of writing down, we would write across and vice versa, we say that A and B are transposes. All right, and we write this capital T that looks like an exponent is saying we're taking the transpose. All right, so for example, if A is the matrix 1, 2, 3, 4, 5, 6, then A transpose, the first column of A is 1, 2, so the first row of A transpose is going to be 1, 2. Right? You see that? We're switching our column, and it becomes a row. Same thing here. 3, 4 is our second column, so now it's our second row. And 5, 6 is our last column, so it becomes our last row. A is a 2 by 3 matrix. A transpose is 3 by 2. Right? Because we switch the rows and columns. So that should switch the dimensions there. All right, let's take a look at an example. All right, so A is going to be the following matrix. 1, 3, 7, 0, 4, 8, and 3, 2, 3. So I want us to first find the value of A 3, 2. So look back in the notes. What do these subscripts mean? Just a yes or no is A square. And then finally, let's find A transpose. All right, so I've said this 1,000 times. Pause the video, try it on your own. All right, flip back in your notes. How do we get this? And then you could just watch me solve it. So welcome back. I'm glad that you paused the video and tried it on your own. A32. So that's saying we're going to go down 3 over 2. Third row, second column, right? That's how you read this. 1, 2, third row, 1, 2, second column. Is A square? Yes, 3 rows, 3 columns. So it's a 3 by 3 matrix, so it's square. And then finally, we want to find A transpose. So remember, to get A transpose, we switch all the rows with columns. So instead of having 1, 3, 7 going down, we're going to have 1, 3, 7 going across. 0, 4, 8. And 3, 2, 3. All right, so it's really not too bad to switch between a matrix and its transpose. We're going to see some examples where it might be useful to add or subtract matrices. And so how do we do that? So if two matrices have the same number of rows and the same number of columns, all right, so if two matrices have the same number of rows and they have the same number of columns, we could add the matrices by adding their corresponding values. All right, so for example, and this, I mean, I know I wrote just, we could add, but subtract as well. So if A is the matrix 1, 4, 2, -1, 3, -2, and B is the matrix -1, -2, 2, 0, -3, 1. These are both 2 by 3 matrices. So they can be added or they can be subtracted from each other. Okay, the new matrix that we're going to get when we do A plus B is still going to be a 2 by 3 matrix. The top left entry is going to be 1 plus -1, 0. 4 plus -2, which is 2. 2 plus 2 is 4. -1 plus 0 is -1. 3 minus 3 is 0. And -2 plus 1 is -1. Now, if the matrices were not of the same size, okay, so let's say C is the matrix 1, 2, 3, 4. C has the same number of rows as A, but it doesn't have the same number of columns. So A plus C does not exist. We need to have the same number of rows and the same number of columns in order to do matrix addition or matrix subtraction. We could also multiply a matrix by a scalar. So you can multiply okay, what is a scalar? It's just a number. All right, and this will give us a new matrix, and it doesn't matter what size we start off with. So if A is the same matrix here, 1, 4, 2, -1, 3, -2, then we can multiply, let's say, 5a. And so what do? We just multiply this to each of the entries. So it's 5, 10, 15, 20, -5, -10. So scalar multiplication is very easy. It's just you take our original matrix and multiply everything by the scalar. All right, let's look at an application. Suppose the prices and delivery costs of various products are given by the following table. All right, so here we have a price and delivery. And we have 3 different products. So we have wood, siding, and roofing. Suppose these are our costs. And, well, like everything, costs go up as things get more expensive. And so suppose costs increase by 10%. All right, so let's write a cost matrix first. So our cost matrix would just be these 6 values, right? 6, 1, 4, 1, 2.5. Okay, so a 10% increase in price is announced. All right, so to get the new cost matrix, basically what we could do, so a 10% increase, that's the same thing as multiplying by 1.1. So our new cost matrix is just 1.1 times our original cost matrix. All right, and so what is that? It's 6.6. 1.1. 4.4, 1.1, 2.2, and 0.55. All right, so this scalar multiplication of a matrix could be interpreted as, what happens if all prices increase by some amount. Okay, one last application of matrices I want to look at is called an adjacency matrix. Okay, so suppose we have a bunch of offices. Suppose this is like some government agency, and there's a bunch of offices, and you could only send paperwork to some of the offices, right? You don't want to send paperwork up to your boss because then they'll get mad at you, all right? So suppose 1 could send paperwork to 2, and 2 could send paperwork back to 1. 2 could send paperwork to 5. 3 could send paperwork to 5. 1 could send paperwork to 3. And so forth. And so we could represent this diagram with a matrix. Okay, maybe it's not immediately obvious, but we can make a matrix that captures all of the information from this diagram. All right, and so how we're going to do that is really not too bad. And so let's construct a matrix A such that, okay, the entries in A, I, J, so these are just the various entries in our matrix, is equal to 1 if room I points to room J, and 0 otherwise. All right, so this diagram we can represent as a matrix. What's the size of our matrix going to be? It's going to be 5 by 5 because there's 5 rooms in our diagram. All right, and now we can fill in our matrix. Does room 1 point to room 1? No, it does not. So we have a 0 in the 1, 1 entry. In the 1, 2 entry, does room 1 point to room 2? Yes. So we have a 1 in the 1, 2 entry. Does 1 point to 3? Yes. Does 1 point to 4? Not directly. So we get a 0 for 1, 4. And does 1 point to 5? No. So this top row tells us where all of the arrows out of 1 go. They go to 2 and 3. Right? You can see that, I mean, sure, this looks nice, but it might be easier for a computer to work with something like this. All right, what would our second row be? Well, it's going to be 0, 0. Sorry, let's try it again. 2 does point to 1. 1, 0. 2 doesn't point to 3. It does point to 4. It does point to 5. What about 3? 3 does not point to 1, does not point to 2, does not point to 3. It does point to 4. It does point to 5. 4 points only to 3. And 5 points to nothing. All right, so this matrix has all of the same information as our initial diagram. So this is another application of how matrices can be useful. Okay, well, I hope you liked today's introduction of matrices. There's way more where that comes from. So I'll see you later. Bye.